Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. I have been discussing about the concept of machine learning. Today I am going to continue the same class, that is the concept of machine learning. So first I will discuss the concept of regression, and after this I will discuss the concept of Bayesian decision theory. So what is the fundamental concept of regression? I will explain now. Linear regression is a statistical method that allows us to model the relationship between the scalar response, that is the dependent variable, and one or more independent variables. So that means I want to find the relationship between a scalar variable, that is the scalar response dependent variable, and one or more independent variables. This is done by fitting a linear equation to the observed data. The dependent variable I can say as a response or outcome, and the independent variable is called as predictor or maybe the regressor. Suppose if we have only one independent variable, this is called the simple linear regression, and suppose if I consider two or more independent variables, then in this case it is the multiple regression. So this method looks for the statistical relationship between the dependent variable and the independent variable. For example, given a temperature in degree Celsius, we can find the exact value of Fahrenheit. Let us now consider the simplest case, that is the simple linear regression. So where we are having only one dependent and one independent variable, and simple linear regression boils down to the problem of line fitting on a 2D xy plane. So suppose the given a set of points in xy plane, x and y coordinates I am considering, the linear regression attempts to find a line in 2D which best fits the points. So that is the concept of the linear regression. The most popular method of fitting a line is the method of least square. So we can consider that method, that is the method of least square. As the name suggests, this method minimizes the sum of the squares of vertical distances from each data point to the line. Now the question is how to find the baseline, and that is the objective of regression. Suppose that the slope and the intercept of the required line are a and b. So I am considering the slope is a and the b is the intercept of the line. Then the equation of the line will be yi is equal to ax I plus b. That is the equation of the line. And the error between the actual point and the line can be determined. So I am determining the error. In this figure, these two figures, I am showing the concept of the polynomial fitting. So you can see observed data, you can see the sample points, the observed data you can see, and I am fitting a curve between these observed sample points, observed data. And same concept I am showing in the second figure also, that is the polynomial fitting. So mainly we want to reduce the error. So these are my observed data, you can see, and this is the curve I am fitting between the observed data points. So the objective is to minimize the error. So that is the objective of regression. So you can see that I can determine the error like this, ei is equal to yi minus yi cap, that I can determine. And the concept of regression is I have to minimize the error. So you can see I can compute the error like this, e is equal to 1 by n. So n number of sample points, suppose yi minus yi whole square, that I am considering the average error I am determining, and this is the expression for e. So the objective is to find the slope a and the intercept b which gives minimum error. So already I have defined a line, and we have the slope is a and the intercept is b. So objective is we have to minimize the error, and corresponding to this we have to determine the slope a and the intercept b. So to find the required values of a and b, we have to consider the partial derivative of e with respect to a and b. So that is the partial derivative of e with respect to a, that should be equal to 0, and partial derivative of e with respect to b, that should be equal to 0. So objective is to find the slope A and intercept B which gives minimum error E. That is the objective. And after this, you can see if I consider this equation, that is the partial derivative of E with respect to A, that is equal to 0. So based on this, I can get this equation. You can do the differentiation. After doing the differentiation, I will be getting this one. And similarly, if I do the partial differentiation of E with respect to B and it is equal to 0, then I will be getting this equation. So I will be getting these two equations, and this equation if I consider suppose equation number 1 and equation number 2. So I am getting two equations. So this equation 1 and 2 are linear equations in two variables. Hence, they can be easily solved to find the values of A and B. The A means the slope and intercept is B. So by solving these two equations, I can determine the value of A and B. A is the slope of the line and B is the intercept that I can determine. So in this case, I have shown only the simple case of linear regression. So if you want to see the polynomial fittings, so you have to see the books. So how to go for polynomial fittings between the observed data points, that you have to see. So in my discussion only I have considered the simplest regression model in which I have only one dependent variable and one independent variable. So this is the fundamental concept of regression. After this, I will consider the Bayesian decision theory. So already I have explained the concept of the Bayes theorem. So here you can see this posterior density, you can see this is the posterior density is equal to likelihood into prior divided by evidence. And if I consider two classes, then the Px will be like this. And in this the Bayesian decision theory, this Px is the normalizing factor. So it has no role in classification, so that we can neglect. So Px is the normalizing factor, that is the evidence. So it has no role in classification. So only we have to consider the likelihood and the prior. So for a particular Fisher vector, the Fisher vector is x, we have to determine the class. So the probability of obtaining a particular class given the Fisher vector is x. So that we have to determine. That is the objective of Bayes decision making. And you can see the decision theory will be like this. So x is the Fisher vector, suppose. So if I consider two classes, the class is suppose W1 and W2, two classes I am considering. If the probability of W1 given x is greater than the probability of W2 given x, then in this case I have to consider the class is W1. And similarly, if I consider the probability of W1 given x is less than the probability of W2 given x, then in this case the corresponding class will be W2. So based on this principle, I can do the classification. Suppose if I have this condition, the probability of W1 given x is equal to probability of W2 x. Then in this case, we have to see the prior probabilities. Suppose this is the condition, the probability of W1 given x is equal to probability of W2 given x. Then in this case, we have to see the probability, that is the prior probability we have to see, probability of W1 and the probability of W2 we have to see, and based on this we can take a classification decision. So how to do the classification now? So you can see, suppose I have the Fisher vector is x, suppose that is the input, and I can determine these values, probability of W1, probability of x W1, probability of W2, probability of x W2, probability of WC, probability of x WC. So I am determining this, and I will be getting probability of W1 x, I will be getting probability of W2 x, probability of WC x I will be getting, and I have to pick the largest one. So out of this, what I have to do? Pick the largest. So out of this, I have to pick the largest. So based on this, I can do the classification. So my input is x. So I can draw the x here, suppose. So my input is x, and I have to determine these values, the probability of W1 given x, the probability of W2 given x, like this I have to determine, and out of this I have to pick the largest, and based on this I can do the classification decision. And also I can determine the probability of error for the given Fisher vector. So what is the probability of error? The probability of error given x is equal to probability of W1 given x. That is, if we decide the class is W2. So if I decide the class W2, then that is the probability of error. The probability of error given x will be probability of W1 given x. And the probability of error given x will be the probability of W2 given x if we decide the class is W1. So like this I can define the probability of error. So we have to minimize the probability of error. So how to minimize this? Decide the class W1 if the probability of W1 given x is greater than probability of W2 x. Otherwise I have to decide the class is W2. So we have to minimize the probability of error, and based on this principle I can minimize the probability of error. I have to minimize the error. So I have to select the appropriate class. The class you can select by these probabilities, the probability of W1 given x and probability of W2 given x, and you can see the average probability of error I can determine like this. So for all the Fisher vectors I can determine the average probability of error, and we have to minimize this error, the probability of error we have to minimize. So how to minimize this error? So this probability of it will be W1 x if x is assigned to this particular class. This is the probability of error. The probability of error is equal to probability of W1 x if x is assigned to this particular class is equal to probability of W2 x if x is assigned to the class is W1. So we have to minimize this probability of error. So we want probability of error given x to be as small as possible for every value of x. So for all the Fisher vectors we have to minimize this error. I can show here. So suppose this is my x is the Fisher vector, and I am considering the probability of x Wi I am considering. So this is suppose the probability of x given Wi, or maybe I can consider suppose two classes. If I consider, it will be W1, and suppose this is the probability of x W2. So this portion, if you see, this is the area of probability error. This is the area of probability error. So this is the concept of the probability of error. So based on the probability of error, we can take a classification decision. And suppose I have C number of classes. So I am considering C number of classes W1, W2, WC, and assume that we have the d-dimensional Fisher vector. So I am considering the d-dimensional Fisher vector I am considering. And if you consider this is the Bayes rule, the probability of Wj given x x is the feature vector, that is the d-dimensional feature vector, is equal to probability of x given wj, that is the likelihood, into probability of wj, that is the prior probability, divided by px, that is the evidence. So we have to compute the posterior probability corresponding to the feature vector x. And for the decision making, what we have to do? So we assign the pattern to the class for which the posterior probability is the greatest, that we can determine. So you can see the same thing I am showing here. So W test is equal to argmax, and I am considering this is the posterior probability is equal to this, and evidence already I have explained, it is nothing but the normalization factor. So it is same for all the classes. So that means it has no role in classification. So how to do the classification? So W test is the class for which the posterior probability is the highest. So based on this, we can do the classification. That means the pattern is assigned to this particular class. So we can determine the posterior probability, and we have to determine the highest value, the highest posterior probability we have to determine, and based on this we can take a classification decision. The pattern is assigned to this particular class. After this, another technique of decision making is by considering the risks. So by considering the risks, we can also take a classification decision. Suppose I have C number of classes. So I am considering the classes W1, W2 like this, WC number of classes, and I am considering some actions. I am considering the actions are alpha 1, alpha 2 like this. I have number of actions, and based on this I can consider the definition of loss. So what is the loss? I will explain. Suppose x is the feature vector and x may belongs to the particular class. I am considering the classes like this. Suppose W1, suppose W2. So W2 is the true class, true state of nature. So the feature vector x may be assigned to the class is W1 or maybe W2 like this, and corresponding to this x belongs to W1, I am taking some actions I am taking. So what are my actions? Action is alpha I am taking, the action alpha I am taking, and corresponding to this I can determine the loss. So what is my loss? Loss is equal to lambda alpha I given Wj, that I can determine. The loss is lambda alpha I given Wj. So particular action is considered, the action is alpha I, corresponding to the class is Wj. So that is the loss I can define like this. So loss is nothing but lambda Ij. That means action alpha I is considered for the class is Wj. So I can show this again. Suppose I have the classes W1, W2 like this. I suppose Wk. So k number of classes, and I am taking the actions like this, alpha naught, alpha 1, alpha k dash I am taking. So these are my classes, and I am taking some actions. Actions are like this, alpha naught, alpha 1 like this. So corresponding to W1 I can take the action alpha naught, and similarly corresponding to W1 I can take this action also. So action is alpha k dash. So corresponding to this, what will be my loss? The loss will be lambda k dash 1. That is the loss I can determine. So this suppose action is the reject option. Suppose this action is the suppose reject option. So in pattern classification, reject option is very important. That means particular feature vector may not be assigned to any one of the classes. Then I can consider the option is the reject option. Suppose in alphabet recognition, so alphabet suppose A, B, C, D like this. Suppose I am writing one alphabet something like this, English alphabet. So that means I have to consider the option is the reject option I have to consider. because it does not belong to any of the classes, that means the alphabets. So this is the concept of the loss. So I can define the loss like this. So action alpha I is considered for the class is Wj, and corresponding to this the loss is lambda ij. So you can see, and from this you can determine the expected loss, and also the conditional risk also we can determine. That is the action alpha I am considering for the Fisher vector. The Fisher vector is x, and that is nothing but the r alpha I given x that I am considering. That is the risk I am determining. This is lambda alpha I given Wj, probability of Wj given x. So this is nothing but lambda ij. This is nothing but lambda ij. At every x, a decision is made, and we have to minimize the expected loss. The concept is we have to minimize the expected loss. So final goal is to minimize the total risks for all the Fisher vectors. So we have to minimize this risks. That is the objective of the risk minimization. So by considering this, we can do the classification. So for two category classification, what we can consider, suppose I am considering the action alpha 1 corresponding to the class is W1, and alpha 2 I am considering corresponding to the class W2, and based on this I can define the loss function. So loss function is lambda ij. So that means action alpha I am considering for the class is Wj, and from this we can determine the conditional risks. So you can see pictorially I can show you like this. Suppose W1, W2, these are the classes, and I am considering the actions alpha 1, alpha 2 like this, and I am taking the actions like this. I am determining the actions. So what is lambda 11? Lambda 11 is nothing but lambda alpha 1 action I am taking corresponding to the class W1, and similarly I can consider lambda 12, lambda 21, and lambda 22. I can consider like this. So I can determine this. After this we can determine the conditional risks. After this we have to minimize the risks. So what will be our decision rule? So if the risks alpha 1 given x is less than risks alpha 2 given x, that is the conditional risks, then in this case we have to consider the action alpha 1 I have to consider. That means we have to consider the class W1 we have to decide, and this is equivalent to this, because from this just you can put these values, you will be getting this one. So we can decide the class W1 if this condition is satisfied. So this is the condition. So we can decide the class W1 if this condition is satisfied. Otherwise we have to consider the class W2. So that is my decision rule. So the previous rule is equivalent to the following rule. So that means we can consider this one. So from the previous equation you will be getting this one. The ratio, the probability of x given W1 divided by probability of x given W2, that ratio we have to determine. If it is greater than this one, so that means if I consider this one, then based on this we can take a classification decision. If this condition is satisfied, then we have to consider the action alpha 1, and what is the corresponding class? The corresponding class is W1. Otherwise we have to take the action is alpha 2, and what is the corresponding class? The class will be W2. So based on this decision rule we can do the classification. So we can select either W1 or W2, and we can also consider this ratio. So this ratio is called the likelihood ratio. This is called the likelihood ratio we can determine. So from the previous slide you can see, so I am considering, suppose this is equal to theta k, and if the likelihood ratio is greater than this threshold, the threshold is suppose theta k, then based on this we can take a classification decision. So if the likelihood ratio is greater than a particular threshold, then in this case we have to consider W1. Otherwise, we have to consider W2. So you can see this likelihood ratio is independent of the Fisher vector. Its likelihood ratio is independent of X. So we can determine the likelihood ratio, and based on this likelihood ratio, we can take a classification decision. So you can see that based on this risks, we can take a classification decision. Now I am defining one function that is called a 0-1 loss function. So suppose actions are decision on classes. So we are taking some actions for decision making. So suppose if action alpha I is taken and the true state of nature is Wj, then the decision is correct if I is equal to j, and the decision is not correct if I is not equal to j. We have to consider this 0-1 loss function, and based on this we can take a classification decision. So objective is to minimize the probability of error. That is the objective. So we have to minimize the probability of error. Now I am defining the 0-1 loss function. So lambda alpha I given Wj I am considering, that is equal to 0 if I is equal to j. So that means the loss will be 0 if I is equal to j. Otherwise, if I is not equal to j, then the 0-1 loss function will be 1. So I am defining this function, 0-1 loss function I am defining. After this, I am considering the conditional risks. So conditional risks already you know. So this is the formula for the conditional risks, and from this you can see I am getting this one, but you can see at this point that j is not equal to I, because when j is not equal to I, the value of 0-1 loss function is 1. So that is why this value will be 1. If j is not equal to I, or if I is not equal to j, that value will be equal to 1, and corresponding to this it is nothing but 1 minus probability of Wi given X. So that is the meaning of this. So to minimize the risks, what I have to consider? I have to select maximum probability of Wi given X. That is the posterior probability I have to select, the maximum value of this I have to select. That means the decision rule will be like this. So decide Wi if probability of Wi given X is greater than probability of Wj given X for I is not equal to j. So this is my decision rule, and this classification technique is called the minimum error rate classification, because I have to minimize the error. So this is called the minimum error rate classification technique. So for minimization of the risks, we have to maximize this probability, since the conditional risk is equal to 1 minus probability of Wi given X, and I have to minimize the error. So what is my classification rule? Decide Wi if probability of Wi given X is greater than probability of Wj given X. So that is my classification rule, and this is the concept of the minimum error rate classification. And based on the discriminant function, I can see the different types of decision surfaces. So this concept I am going to explain. So what is the discriminant function, and from this how to determine the decision boundaries, the decision surfaces. So let us consider the multi-category case. So multiple classes I am considering, and for this I am considering the discriminant function. The discriminant function is Gix I am considering, and for each and every class I have to determine the discriminant function. So I have to determine G1x, G2x, G3x, like this. For all the classes I have to determine the discriminant function. The classifier assigns a feature vector x to a particular class. The class is suppose Wi if Gix is greater than Gjx. For j is not equal to I. So based on the discriminant function, I can take a classification decision. That means if gix is greater than gjx, now based on this, I can decide the class. The class is wi. That means the feature vector x will be assigned to the class is wi. And here you can see I am considering the input feature vector. The input feature vector is the d-dimensional feature vector. So this is my x, that is the feature vector. So this is the d-dimensional feature vector I am considering. So that means x1, x2 like this. So this is the d-dimensional feature vector I am considering. And after this you can see I am determining the discriminant function for all the classes. So I am considering c number of classes. So I am determining g1x, g2x like this I am determining. And for classification, what we have to consider, I have to find the maximum discriminant function I have to determine. So out of this g1x, g2x, gcx, which one is the maximum I have to determine for classification. So you can see, so I am determining the cost. That means I have to find the maximum discriminant function, and based on this I can take a classification decision. So what is the function of the discriminant function? It divides the feature space into C decision regions. The decision regions are R1, R2 like this. These are the decision regions RC. And if GIX is greater than GJX for I is not equal to j, then X is in the region, X is in the region Ri. That means the meaning is X is assigned to the class is Wi. So that is the decision rule. And what is the decision boundary? The decision boundary is nothing but Gix is equal to Gjx. So that is the equation of the decision boundary. So for C number of classes, we have to determine C number of discriminant functions. So you can see I have to determine the maximum value of the discriminant function that corresponds to the minimum risks. So maximum discriminant function corresponds to minimum risks. So that means for minimum error rate, Gix should be equal to Pwix, that is the posterior probability. So that means the maximum discriminant function corresponds to maximum posterior probability. So I am repeating this, the maximum discriminant function corresponds to maximum posterior probability. And what is the posterior probability? If you see, this is nothing but it is equal to probability of x wi, probability of wi, probability of x, and that I can write like this. So from this I can write like this, because the evidence has no role in classification. So I can write like this. After this I can take the natural logarithm, because the multiplication is converted into addition by considering the logarithm. So I have this discriminant function Gix is equal to this. So discriminant function do not change the decision when scaled by some positive constant. So if it is scaled by some positive constant, the discriminant function do not change the decision. The decision is not affected when a constant is added to all the discriminant function. So that is the concept of the discriminant function. So if I consider two classes, suppose, so for first class, suppose the discriminant function is g1x. For the second class, suppose the discriminant function is g2x. Then what will be my classification rule? If g1x is greater than g2x, then means that the meaning is x will be assigned to the class is w1. And what will be my decision boundary? The decision boundary will be g1x is equal to g2x. So that is the equation of the decision boundary. So this is my decision boundary. So this equation, that means g1x minus g2x is equal to 0. That is the equation of the decision boundary. So I can write like this, that means gx is equal to 0. So that is the equation of the curve. That is the equation of the curve. So if I consider these two classes, so if I consider this is the Fisher space, so I have two regions, the region is R1, another region is R2, and what will be the equation of the decision boundary? The equation of the decision boundary is gx is equal to 0, and that is the equation of the curve, or maybe in this case I am considering the line, that is the decision boundary. I am considering the line, I am considering two regions R1 and R2, and in the region R1 gx is greater than 0, and in the region R2 gx is less than 0. So gx is greater than 0 means I am considering the class W1, and gx is less than 0, that means I am considering the class W2. The Fisher space is divided into C number of regions, C decision regions, and if gix is greater than gjx, for j is not equal to I, then x is in Ri, that means the Fisher vector will be in the region Ri. That means the Fisher vector x will be assigned to the class is Wi. And for two category case, that is that for two classes, I have to determine g1 and g2, and gx is equal to g1x minus g2x, and we can take a classification decision based on this condition. So decide W1 if gx is greater than 0, otherwise decide W2. That we have to consider. And this gix, already I have this equation, the equation of the discriminant function, and corresponding to this you can see this gx is nothing but pw1x minus pw2x, that is the gx. Gx is nothing but g1x minus g2x. And from this, if you can put this value, because this what is pw1x, what is pw1 given x, that is nothing but px w1 and pw1, and the evidence is suppose px. So if I put this value in this equation, then you will be getting this one. So you can get this one. So we have to determine gx, and similarly also you have the another one pw2x. So pw2 also x we can determine. So if I put these two values, you will be getting gx. So gx is nothing but g1x minus g2x. So this is nothing but g1x minus g2x. Now I will discuss the concept of normal distribution. So already you know what is normal distribution. So here you see I am showing the density function corresponding to the normal distribution. Px is equal to 1 by root over twice pi sigma square e to the power minus half x minus mu sigma whole square. So that is the normal distribution, and corresponding to this you can see I have the bell shape distribution. So this is the bell shape distribution corresponding to that PDF. That PDF is Px, and corresponding to this I have the probability density function, and this is the normal distribution with mean 0. So here you can see the mean is 0, and from this you can determine the expected value or the mean value of x. So I can determine the mean of this random variable. So Ex I can determine. Also I can determine the variance of x. So in this case, suppose I am considering, suppose this variance is suppose sigma 1 square, and suppose I am considering another Gaussian function, something like this. Then in this case, suppose the variance is sigma 2 square. So in this case, the sigma 1 is greater, sigma 1 square is greater than sigma 2 square. So you can see that the variance determines the spread of the Gaussian function. So this is about the normal and the Gaussian distribution. Now let us consider the multivariate Gaussian distribution. So I am considering the vector. Vector is the d-dimensional vector. So x is the d-dimensional vector, x1, x2 like this. So this is the d-dimensional vector. Corresponding to this, I can define the density function. The density function is px, and this is for the multivariate Gaussian distribution. So in this case, I have two parameters. One is the mean vector and another one is the covariance matrix. So I have two parameters. One is the mean vector, another one is the covariance. I can determine the mean vector from the input vector. The input vector is x. So the mean vector is nothing but mu is equal to mu1, mu2, mu3. And since I am considering the d-dimensional vector, so this is the mean vector. That means I can determine the expected value x1, x2 like this I can determine. So mean vector I can determine, and also I can determine the covariance matrix. So this is my covariance matrix. So this is expected value x minus mu transpose. So you can see I can determine the covariance matrix. And if I consider the dimension is suppose 1, so suppose the dimension of the Fisher vector is 1, then in this case I will be getting the univariate density. So what is the univariate density? That is already I have defined. The univariate density is twice by sigma so I will get the univariate density corresponding to d is equal to 1. So in this case I have two parameters. One is the mean, another one is the variance. So for univariate case, I have two parameters. One is the mean, another one is variance. So in this case, you can see I am considering the d-dimensional Fisher vector, and from this I can determine the mean vector, and also I can determine the d by d covariance matrix. So in this slide, you can see how to determine the covariance matrix. So the covariance matrix, you can see expected value of this, expected value of x I minus mu I, xj minus mu j, that I can determine. So that means the covariance between xi and the xj I can determine. So this is my covariance matrix. And the diagonal elements sigma ij are the variance of the respective xi. So if I see the diagonal elements, that is nothing but the variance of respective xi. So that means sigma I square, that corresponds to the variances of respective xi. And if I consider the off diagonal elements, that means these off diagonal elements. So off diagonal elements are sigma ij. So these are the covariance between xi and xj. So that is the covariance between xi and the xj. And if I consider, suppose if xi and the xj are statistically independent, what is the meaning of this? That means sigma ij is equal to 0. That is the covariance is equal to 0. That means xi and the xj are statistically independent. Then corresponding to this px that already I have defined, that will be the univariate density. Univariate normal density. So that will be the univariate normal density. So that means if xi and xj are statistically independent, that corresponds to sigma ij is equal to 0, and that corresponds to px will be the univariate normal density. Now I can define a distance. So what is the distance? You can see I am considering the distance x minus mu transpose so I have this distance r square is equal to x minus mu transpose sigma to the power minus 1 x minus mu. So in this case you can see this corresponds to the determinate and this corresponds to the inverse of the covariance matrix. So this corresponds to inverse of the covariance matrix. So I am defining a distance that is r square is equal to x minus mu transpose and sigma to the power minus 1, that is the inverse of the covariance matrix x minus mu, and that distance is called, that is a very important distance, this is called the squared Mahalanobis distance. The Mahalanobis distance squared Mahalanobis distance. Already you know that what is the Euclidean distance? The Euclidean distance is nothing but the distance between the vector x and mu I, suppose. So this is the Euclidean norm. So this is the Euclidean norm, and I have shown that this is the Mahalanobis distance. So in case of the multivariate density, the center, that means in this case if I consider a cluster, suppose I am considering some sample points I am considering. So this is a cluster. The center of the cluster is determined by the mean vector, and the shape of the cluster is determined by the covariance matrix. So that is the importance of the mean and the covariance. So if I consider a cluster, I am considering some sample points. So the center of the cluster is determined by the mean vector, and the shape of the cluster is determined by the covariance matrix. Now I am discussing the concept of the Bayesian classification for normal distribution. So let us discuss about the concept of the Bayesian classification for normal distribution. So let us discuss about this concept, the Bayesian classification for normal distribution. So in case of the Bayes classifier, so I have to determine this. So this is nothing but PWJX is equal to PXWJ, PWJ and PX. So this is the Bayes law. So for determining the probability of Wj given X, I have to consider this, that is the likelihood or the class conditional density I have to consider. Suppose the class conditional density follows the normal distribution. So that means the likelihood function Wi with respect to X in L dimensional feature space follow the general multivariate normal density. So that means the probability of X Wj, I am considering the density is suppose the normal density, and in this case I am considering multivariate normal density. So that means the probability of X given Wj is a multivariate normal distribution, and I am considering the Fisher vector, that is the L dimensional Fisher vector. So L dimensional Fisher vector I am considering. So twice pi to the power L by 2 sigma I to the power half and exponential minus half x minus mu I transpose so I am considering the multivariate normal distribution and I am considering C number of classes. So that covariance matrix for a particular class. So that means I am considering the covariance matrix for the class I. So that is the dimension is L by L covariance matrix I will be getting. Also I can determine the mean vector. So mu I also I can determine, that is a mean vector I can determine, that is nothing but the expected value of x I can determine. Now you know the discriminant function gix is equal to log you know this. So in this case I think better I should write wi, that is x given wi I am writing. In place of wj I am writing just the wi. So this is the discriminant function. So if I consider this multivariate normal distribution, so just I have to put this value here. So I will be getting minus half x minus mu I transpose the covariance matrix for the class I plus Ci. So suppose this is equation number 1. This Ci is a constant. So what is the value of this constant? L divided by 2 ln twice pi minus half ln. So this is Ci. So I can expand gix, that is the discriminant function. So if I expand gix, it will be something like this, minus half x transpose mu I t. Just I am expanding. So suppose this is the equation number 2. This is the equation number 2. So I am getting the expression for the discriminant function, and in this case what I am considering, the probability of x given wi that follows the multivariate normal distribution. So based on this I am calculating the discriminant function. The discriminant function is gix. What will be my decision boundary? So my decision boundary or decision curves, the decision curves will be gix is minus gjx is equal to 0. So that is the decision boundary. So this decision boundary may be the quadratic decision boundary, because this is a quadratic equation. So if you see this one, so this is a quadratic equation. So that is why this is called a quadratic classifier. Bayesian classifier is also called quadratic classifier because this is a quadratic equation. So decision boundary will be quadrics. So decision boundary may be like this, ellipsoid, or maybe the parabolas, or maybe the hyperparabolas, or maybe the pairs of lines I can consider. Like this, I have the quadrics decision boundary. So this equation number 2 is the quadratic equation. So that is why the Bayesian classifier, the Bayesian classifier is also called the quadratic classifier. So if I consider the two-dimensional case, so decision boundaries may be something like this. So this will be one class and this will be another class. Or maybe the non-linear, maybe the decision boundaries may be something like this. So this is suppose W1, this is W2 and W1. So this is X1 and X2. So two-dimensional Fisher vector I am considering, and for this I may have this type of decision boundaries. So if I consider high dimensional case, then in this case I will be getting hyper ellipsoid, hyperparabolas, like this I will be getting. Now what about the decision hyperplanes? So if I consider equation number 2, you can see the equation number 2. In equation number 2, you will be having this term xt sigma I to the power 1 and x, this in equation number 2. It is same for all the discriminant function. It is same for all the discriminant function. So that means it has no role in classification. So that means I can neglect this one. And suppose if I consider this case, the covariance matrix is same for all the classes. The covariance matrix is same for all the classes, but it is arbitrary. So that I am considering now. So this quadratic term is same for all the classes. Same for all the classes. So that means I can neglect this one. It has no role in classification. And I am considering this case, that is the covariance matrix is same for all the classes, but it is arbitrary. So that is why I can write the discriminant function something like this. Gix is equal to Wit x plus Wi0. So this Wi is, this is called the weight vector. This is called the weight vector, and this is I can consider as bias or the threshold. So bias or threshold I can consider like this. So what is the weight vector? Wi. Wi is equal to sigma to the power minus 1 mu I. So that is the weight vector. And what is the bias? The bias is nothing but Wi0, that is equal to log n log Pwi minus 1 by 2 mu I t sigma I mu I. So here you can see, if I see this expression, that is the discriminant function gix is a linear function of x, and in this case the decision surfaces will be hyperplanes. So I am repeating this, that is the discriminant function gix is a linear function of x. X is the input Fisher vector, and corresponding to this the decision surfaces will be hyperplanes. Now let us consider two cases. Case number 1, I am considering the covariance matrix is same for all the classes, and it is the diagonal covariance matrix. So that means what I am considering, the diagonal covariance matrix with equal elements. So what is the meaning of this? The Fisher vector is mutually uncorrelated and of some variance. So that means I am considering a diagonal covariance matrix with equal elements. The meaning is Fisher vector is mutually uncorrelated and of same variance. And in this case you can see what is the I? I is the identity matrix. So it is the L dimensional identity matrix. So I is the L dimensional identity matrix. And suppose this equation is, suppose I am considering the equation is 3, suppose. So from 3, equation number 3, what I will be getting now, gix will be equal to 1 by sigma square mu I t x plus wi. So I will be getting wi 0, that is the bias. And in this case, what is sigma to the power minus 1? That is the inverse of the covariance matrix, 1 by sigma square I. I is the identity matrix. So what will be the decision hyperplanes? Decision hyperplanes will be gij x is equal to gix minus gj x. So that is nothing but wt x minus x naught. This you can verify like this. Suppose wt x1 plus w naught is equal to wt x2 plus w naught. So corresponding to this, what I will be getting wt x1 minus x2 is equal to 0. So like this you can verify that one. So this is the equation, that is the equation, what is the equation of the decision hyperplanes? Gij x is equal to wt, that is the weight vector, x minus x naught. So this is the equation of the decision hyperplanes. And in this case, what is the weight vector? The weight vector is nothing but mu I minus mu j. That is the weight vector, mu I minus mu j. And the x naught is equal to 1 by 2 mu I plus mu j minus sigma square So that is x naught. So the decision surface is a hyperplane which will pass through the point. The point is x naught. So I am repeating this. In this case, the decision surface is a hyperplane passing through the point. The point is x naught. And suppose if I consider if the probability of Wi, if suppose the probability of Wi is equal to probability of Wj, then in this case, corresponding to this, the point x naught will be 1 by 2 mu I plus mu j. So that is the decision surface, and the point will be x naught is equal to 1 by 2 mu I plus mu j. That means the hyperplane passes through the mean of mu I and mu j. So in this case, if the probability of a particular class, the class is Wi, is equal to probability of the another class, and the class is Wj, and in this case I is not equal to j, then x naught is equal to 1 by 2 mu I plus mu j. So that means the hyperplane will pass through the mean of mu I and mu j. And also the hyperplane will be orthogonal to the vector. The vector is w is equal to mu I minus mu j. So that I will show pictorially. And suppose if the probability of Wi is less than probability of Wj, then what will happen? The hyperplane will be located closer to mu I. That is, the hyperplane will be located closer to the mean vector. The mean vector is mu I. And also, if the probability of Wi is greater than probability of Wj, then what will happen in this case? The hyperplane will be located closer to mu j. That is the mean Wj. So this is the case. And if the variance is sigma square is small, if the variance is small with respect to the difference in the mean, so I am just finding the Euclidean distance between these two means, the location of the hyperplane is rather insensitive to the values of Pwi and Pwj. So I am repeating this. If the variance is small with respect to the difference in the mean, the location of the hyperplane is insensitive to the values of the probability. The probability is probability of Wi and the probability of Wj. So these conditions I will be showing pictorially. So what will be my decision boundary? So I can show the decision boundary like this. So suppose if I consider the two-dimensional feature space x1 and x2. So suppose this is my mean vector. Suppose this is mean vector is mu I, and this is mu j. Suppose this vector, and I can find the vector mu I minus mu j. That is nothing but the weight vector. And also you can see I can determine the point. The point is nothing but x naught. I can determine. So from that equations you can determine the point x naught. So that means the hyperplane will pass through the point. The point is x naught. And if I consider the probability of Wi is equal to probability of Wj, then x naught is equal to 1 by 2 mu I plus mu j. That already I have calculated. So that means the hyperplane will pass through the mean of mu I and mu j. And also the hyperplane is orthogonal to the vector w. So that means if I consider a hyperplane, so hyperplane is this, suppose. So this is my hyperplane. So that will be orthogonal. So maybe I can consider some another color that you can understand. So this is my hyperplane. So hyperplane is orthogonal, so it is orthogonal to the vector is W. The hyperplane will be orthogonal to the vector mu I minus mu j. So this is mu I minus mu j. And in this case, what I am considering, the sigma is equal to sigma square I. That means the covariance, I am considering the diagonal covariance matrix with equal elements. So diagonal covariance matrix I am considering. And if I consider these two cases, one is the high variance, another one is the low variance, the small variance. So what will happen, you can see. So this is mean of the cluster. Suppose if I consider this the cluster. So the mean of the cluster is mu I, and another cluster I am considering. So this is another cluster. So this is mu j. And from this you can see already I have shown you. So you can determine the vector. The vector is mu I minus mu j. That you can determine. That is nothing but the weight vector, W weight vector. And after this, you can draw the decision boundary. So this is my decision boundary. You can draw. That is orthogonal to the vector W, and it will pass through the point x naught. So in this case, I am considering the compact case. This is the compact case. That means I am considering the samples with high probability. The samples with high probability. Samples with high probability. I can consider another case, that is the non-compact case. So in the non-compact case also I can draw the decision boundary. So in case of the non-compact case, again like the previous case, I can draw the mean vector mu I and the mu j. And if I consider this is the cluster, suppose the mu j is something like this. So this is mu j, and you can determine mu I minus mu j, and in this case also you can determine the decision boundary. So you can find the decision boundary. So decision boundary will be something like this. So this is the non-compact case. That means sigma square is large. In the previous case, the sigma square is small with respect to mu I minus mu j. So that means in the second case, the location of the decision hyperplane is much more critical as compared to the first case. The first case is the compact case. So in the compact case, you can easily draw the decision boundary between these two clusters. But in case of the non-compact case, so non-compact case I am showing in the second case. So it is very difficult to draw the decision boundary. So location of the decision hyperplane is much more critical as compared to the first case. This is about the representation of the decision boundary. Now I am considering the case number 2, case 2. So I am considering the non-diagonal covariance matrix. So I am considering the non-diagonal covariance matrix. This is a case number 2. That means the sigma I is equal to sigma. The covariance matrix is same for all the classes. In case of the case number 1, what I am considering diagonal covariance matrix. But in this case, I am considering the non-diagonal covariance matrix. So corresponding to this, the decision boundary will be Gix is equal to Wt x minus x naught is equal to 0. And what will be my weight vector? The weight vector will be sigma to the power minus 1. That is the inverse of the covariance matrix, mu I minus mu j. And the x naught, the decision boundary will pass through the point. The point is x naught 1 by 2 mu I plus mu j. minus ln So decision boundary I can find like this. So I can calculate the weight vector and also I can determine the point. The point is x naught. So the decision boundary will pass through the point x naught. But in this case, the hyperplane is no longer orthogonal to the vector w. That is the case for the non-diagonal covariance matrix. Now let us consider the concept of the minimum distance classifier. So what is the minimum distance classifier? Minimum distance classifier. Let us consider. So what is the minimum distance classifier? So from the equation number 1, you have seen that the discriminant function is equal to minus 1 by 2 x minus mu I transpose and sigma to the power minus 1, that is the inverse of the covariance matrix. So you know this. So suppose the case like this. So sigma is equal to sigma square into I. So I is the identity matrix. So in this case, I have to determine the maximum discriminant function. So for C number of classes, I have C number of discriminant function and I have to take the decision based on this. So I have to find the maximum discriminant function and based on this, I have to take the classification decision. So that means the maximum discriminant function means minimum Euclidean distance between the respective mean points. So what is the Euclidean distance? The Euclidean distance dE, I can write like this. This is the Euclidean distance between the vector x and the mean mu I. So that I have to find. So that means the maximum discriminant function corresponds to minimum Euclidean distance. So I have to find the Euclidean distance, and what is the classification decision? I have to find the maximum discriminant function that corresponds to minimum Euclidean distance from the respective mean points. And suppose if I consider the Euclidean distance is equal to constant, then in this case I will be getting the curves of the circle. I will be getting. So maybe I can get the curves of the circle in case of the two-dimensional case, and if I consider the high dimensional case, I will be getting hypersphere. So that is the Euclidean distance contour I can determine. So corresponding to this, I can draw this. So these are my contours. That means contours of equal Euclidean distance. So two classes I can consider. The contours of equal Euclidean distance, and you can see this vector is the weight vector. So suppose this is a class 1 and this is a class 2, and I can draw the decision boundary. So this is the decision boundary between these two classes. This is the decision boundary. So if I consider the two-dimensional case, then in this case, I will be getting the curves of circle, and if I consider the high dimensional case, then I will be getting the hypersphere. So these are nothing but the contours of equal Euclidean distance. The Euclidean distance is dE, the contours of equal Euclidean distance. The second case, what I am considering, the second case is non-diagonal covariance matrix. I am considering the non-diagonal covariance matrix. So that means in this case also I have to maximize the discriminant function. So maximizing the discriminant function is equivalent to minimizing the covariance matrix norm. So that means I have to maximize the discriminant function GIX. that corresponds to the minimization of sigma to the power minus 1 that I have to minimize. So for this, I can determine the Mahalanobis distance. So already I have defined the Mahalanobis distance. So x minus mu I t x minus mu I one by 2. So I can determine the Mahalanobis distance. So the minimum distance corresponds to the maximum discriminant function. And if I consider dm is equal to c, then in this case I will be getting the contours. So maybe I can get the curves of ellipse. So for the high dimensional case, I can consider the hyperellipsoid, and for the 2-dimensional case, I will be getting the ellipse, the contour of the ellipse. So maybe something like this I will be getting. In the previous case, I have the curves of the circles. Now I will be getting the curves of the ellipse. The ellipse will be like this. This is for the clusters 1, and similarly for the cluster 2 also, I will be getting the curves of the ellipse, and this is the vector mu I minus mu j, because I have to determine that this mu I and mu j. So this is mu I and mu j, and in this case already I have defined that your decision boundary, the decision boundary will not be orthogonal. It will not be orthogonal to this vector. This vector is nothing but mu I minus mu j. This vector is mu I minus mu j. So you can see, so I have considered the minimum distance classifier based on these two distances. One is the Euclidean distance, another one is the Mahalanobis distance. In this class, I discussed the concept of the Bayesian classification. First, I discussed the concept of probability of error, and after this, I discussed the concept of risks. So by considering the probability of error, I can take a classification decision. Similarly, by considering the risks, I can also take a classification decision. After this, I discussed the concept of discriminant function. So for C number of classes, I have C number of discriminant functions, and based on this discriminant function, I can take a classification decision. After this, I consider the normal distribution. One is the univariate distribution, another one is the multivariate normal distribution. After this, I determine the discriminant function. The discriminant function is GIX. And after this, I consider two cases. One is the diagonal covariance matrix, and another one is the non-diagonal covariance matrix. For this, I determine the decision boundary. In one case, the decision boundary will be orthogonal to the vector W, that is the weight vector. And in the second case, the decision boundary is not orthogonal to the weight vector. The weight vector is mu I minus mu j. And after this, I discussed the concept of the minimum distance classifier. So let me stop here today. Thank you.